I am so excited to talk to you about entropy today. Entropy is just one of my favorite concepts to talk about because it's the measure of chaos or the measure of disorder in a system. And of course, it's not really measuring chaos because you can't really quantify such things. As a scientist, I can't say such things, but I get really excited about them because of the concept. So entropy, which has the symbol of S for reasons that I don't understand, is the measure of how dispersed the energy is in the system. So if we are, spreading out the energy of a system, then the more spread out it is, the more distributed the energy is in that system, then the happier the system is. It's kind of counterintuitive in some ways about entropy. But think about it like my messy apartment. You probably haven't been to my messy apartment, but you can picture it in your mind here, hopefully, if I do the right thing storytelling-wise. Okay, so if when I get home from a long day, then I am going to get out of my work clothes, right? And I can either take the time to put my work clothes back on hangers and put them into the closet and close the closet door, right? Or I can just take off my clothes from work and throw them into a pile, right? Those are kind of my options, right? There's probably something in between, but those are the two options. Which one takes less energy, right? Which one do I have to put less energy into? Well, obviously throwing them in a wad on the floor takes less energy than hanging them into my closet. So which one am I going to do? Then I'm going to do the lowest energy. I'm already tired. I'm a system that's already been doing some work. And now I'm just going to do the lowest energy option possible. Think about my dishes. I don't look in my kitchen right now. But I can either take my dishes and I wash them and I put them away at the end of the day, and then I have everything in their cupboard and everything is stacked and I can put in all of the energy to do that, or I can leave them in piles in my sink for them to rot, right? Those are the options. So the lowest energy option is to not put my dishes away, to let my clothes be in wads on the floor. And if I'm thinking about this in terms of the energy of the system or the entropy of the system, then that's a good thing. That is the natural tendency. There's a natural drive towards disorder in a system, because if I don't put any energy into the system, then the natural tendency is towards disorder. And that actually relates to the second law of thermodynamics. So the second law of thermodynamics is all about entropy, and it just says that, in a closed system, the natural drive is going to be towards the lowest energy possible, which is going to be about this dispersion or spreading out of energy. Okay, now in a chemical context, we can think about entropy in a couple different ways. It's all about kind of reactants to products, order to disorder, or disorder to order, and kind of which one is better, at least from an entropy standpoint, is if I'm going from a more ordered system to a less ordered system or a more chaotic system, that's a good thing. And if I'm thinking about going from reactants to products, I'm looking at not just S, I'm looking at S on each side and looking at the change in S. So if I was going to look at the delta S for something that's more ordered to more disordered, the disordered is favorable. It would have a higher entropy value, a higher S. So that would give me a positive value. So if my products are more disordered than my reactants, then my delta S, that looks like a mountain, not a delta, is going to be positive. And kind of the opposite is true when I go from more disorder to order. And even just kind of go back to my messy apartment. If I wanted to make order out of all of that disorder, then I would have to put energy in order to make that happen. And so that's going to be a negative thing, at least for the system and for me as well. Okay, now, we're scientists, so we care about measuring things, and what the units are going to be important. The standard units for entropy are joules per Kelvin, or JK, which I always joke that I'm not kidding about. joules per Kelvin. You could talk about it in kilojoules per Kelvin. You could talk about it in terms of degrees Celsius as well. But we know that Kelvin is kind of our absolute temperature. It's our standard for temperature, so we usually stick with that. The fact that it's in joules is sometimes a sticking point for students, especially as you're solving problems for these types, because you're often given other units, kilojoules, for example, for enthalpy. So you want to make sure that you have the same energy units for all of your various thermodynamic quantities, but your SI units for entropy and the way they will be reported in thermodynamic tables are in joules per Kelvin. Okay, so we've already talked about it a little bit with respect to my apartment, but let's think about it in terms of phase changes. So now if we're thinking about a physical change going from one state of matter to another, then let's think about kind of the disorder here. So if I'm going from a solid to a liquid, is that going to have a positive or a negative delta S? Am I going to more order or to more disorder? Well, going from a solid to a liquid, we know a liquid is more disordered, right? The particles can move past each other. It's a fluid as opposed to a solid, which has rigid structure. So I'm going to a more disordered state, which is a good thing, which would give me a positive delta S. How about a gas to a liquid? If I take the gas particles and I condense them down, right, condensation into a liquid, I'm making a more ordered phase, right, than my gas is. My gas is my most disordered phase. So that's going to be a negative change in my entropy, right? I'm creating more order from the disorder. If I go from a liquid to a solid, so now I'm freezing something, right? So I take water and I put it in my freezer, and I put my a more ordered state out of my liquid, then that's going to be a negative delta S. And if I'm going from a solid to a gas, so think, carbon dioxide, dry ice, we're sublimating, we're going directly to the gas phase. This is going to be a pretty big change in entropy because we're going from the most ordered phase to the least ordered phase. This is a good thing, right? This is energetically favorable and would have a positive change in entropy, positive delta S. Okay. So let's think about this in terms of the equation then. At equilibrium, if we're thinking about units of joules per Kelvin, then it has to be some sort of energy per temperature, right? So at equilibrium for a system, or for a system at equilibrium, however you want to say it, the change in entropy is equal to the heat, that's our Q, over the absolute temperature. And we know that the heat of a chemical reaction is equal to the change in enthalpy, right? So we've talked about this before in thermodynamics, that heat is related to enthalpy, or at least the change in enthalpy. So we could also think about our delta S as delta H over T. Again, at equilibrium. We'll talk about non-equilibrium kind of processes and non-equilibrium entropies and how all that works in future videos, but for right now, let's focus on equilibrium. Okay, so this is our equation. When I look at the change in entropy, then that's going to give me an energy unit here. Usually, again, our enthalpy is in kilojoules over our temperature, which is going to be in Kelvin. So if we were going to report this at the end in our SI unit, we would have to convert to joules. So let's do that. Let's look at the problem. I should have had this mapped out in advance, but whatever. I do what I want. Increasing the entropy of my lecture videos here. Okay. So let me give you some info. If I was looking this up in thermodynamic tables, then we know that our thermodynamic quantities are at 25 degrees Celsius. Then I have carbon tetrachloride, goes from a liquid to a gas with a delta H, which in this case, liquid to a gas is vaporization, right, of 39.4 kilojoules per mole. So I went to the thermodynamic tables, and that's what I found, that in order to evaporate my carbon tetrachloride, that's the amount of energy that would require to do so. So here's the problem. So if I have 1 mole at 25 degrees Celsius, and I looked up the entropy, again, this is something you can look up in chemical tables. And I should have had that written down in advance, I apologize. Okay, so 25 degrees Celsius, I have carbon tetrachloride. This is my information about my delta H. So this is the delta H of the phase change going from the liquid to the gas. So it's the delta H of vaporization, which has this amount of energy. Now, the question is saying, well, I have 1 mole of carbon tetrachloride in the liquid phase, and I looked it up, and the entropy is 216 joules per Kelvin. But if I was at that same temperature, what would the entropy of 1 mole of gas of that be? So we can solve the problem by saying, well, we know this relationship between my delta S and my delta H. My delta S is equal to delta H over T. And in this case, because we're talking about the phase change, this is going to be our delta H vap. It could be, you know, the delta H of fusion if we're talking about going from a solid to a liquid. It could be the delta H of formation if we're talking about creating compounds and going from reactants to products. So our subscript here just refers to the fact that we're talking about a phase change in our problem solving. So the delta H vap is given. I'm going to convert it to joules. So I know then it's not pretty, but it'll do. The temperature here I'm converting to Kelvin. So remember, our magic number to convert to Kelvin is 273.15. So I add that to my 25 degrees Celsius. I have to round to the ones place in terms of significant figures. So that gives me a delta S of 132 joules per mole Kelvin. All right. Wow, my handwriting is atrocious. All right. So our delta H, our delta S, our change in the entropy is 132 joules per mole Kelvin. So that is interesting information, but it doesn't answer the question, right? The question is, what is the entropy of that carbon tetrachloride at that temperature? So this gives me the change. This is how different the gaseous phase would be from the liquid phase, but it doesn't give me my actual number. If I was to say, well, it's 132, then that wouldn't make a lot of sense, right? Because the entropy of the liquid is 216 joules per Kelvin. And we would expect then the value of the entropy, based on what we've just been talking about, of the gas phase to be greater, right? It's a greater amount of disorder. There's a greater amount of dispersion of the energy in the gas phase than the liquid phase. So we're expecting this number to be larger. When I look at this here, right, because of these values, because of this delta H, which is positive, right, and it makes sense that it's positive, right, I have to put energy in order to go from a liquid to a gas, right, so it's an endothermic kind of process if you want to think about it that way. So because delta H is positive, and with the way that this is set up, this is also giving me a positive entropy then, right, so that positive entropy means I'm getting more disordered. And if this is my change, this positive change in entropy, then in order to get the entropy for my gas phase, that's going to have to be equal to the entropy of my liquid phase, and then plus this change. Right? Or if it was negative, then it would be minus that change, and that would give me the new. But we would expect it to be a greater quantity. We expect it to be positive because we're getting to a more disordered phase. So if we plug that in, we're going to put our 216 here. Then we end up with 348 joules per Kelvin. All right, and again, kind of that back of the envelope, does this make sense? It's a number that's greater than what I started with, which makes sense from a problem solving standpoint. In terms of significant figures, it looks like I have 3 along the way. This 1 mole per 1 mole is kind of a count, right? This is kind of a per mole sort of situation. So we can have as many significant figures as we want here. The temperature, when you change it to Kelvin, when you convert it to Kelvin, is going to have 3 significant figures. And then the original delta H has 3 significant figures as well. So we'll have 3 significant figures in our answer. The magnitude makes sense, and that's going to be your answer for this type of problem.